Welcome to fourth lecture under the topic flow of water through soils. In the previous lecture, we have discussed about fluid flow through soils and flow of water through a porous media. Then we also discussed about changes in geostatic stresses with the flow of water through soil, and we have introduced an upward flow condition, a flow condition which is defined as a quicksand condition, and we have looked into some typical examples governing the quicksand condition. In this lecture, we are going to learn about factors affecting the permeability. Before discussing about the factors affecting permeability, let us look into the methods which are available for measuring permeability in the laboratory. As discussed, as introduced in the previous lecture, permeability can be measured in the laboratory as well as in the field. For the field, we have got a specific methods which are required to be executed to compare the laboratory permeability or sometimes to assess the permeability under in situ conditions. Now, in this particular lecture, we are going to study about flow of water through soils, particularly the measurement and then their factors affecting this coefficient of permeability, which is nothing but the Darcy's coefficient of permeability. Before looking into this, this particular problem is given to practice as a continuation of the previously solved problems. In this, problem statement is as follows: determine and plot the total vertical stress, pore water pressure and effective vertical stress distribution at levels A, B and C shown in this cross sectional diagram. So, here in this slide, the two layers of soils are shown. The upper layer is silty clay having specific gravity of solids as 2.7, natural water content as 45.2%, and the coarse sand which is lying below this silty clay is under artesian conditions. So, the head of the water above this natural groundwater table is 4 meters. So, by keeping in view of the concepts already introduced, first determine the total vertical stress at points A, B and C or at elevations A, B and C. Then, considering the flow taking place in the vertical direction, determine the pore water pressure at A, at B and at C. Then, subtracting pore water pressure from total stress, determine the effective stress. And from the given data, it is also possible to estimate seepage velocity. So, this can be estimated by knowing coefficient of permeability. Let us consider the coefficient of permeability for this type of soil is say 1 into 10 to the power of -7 meter per second. By knowing the hydraulic gradient or with which the flow is occurring, we can compute the discharge velocity or superficial velocity, which is V is equal to K I. By knowing the natural void ratio or the void ratio from the water content, W is equal to 45.2% and specific gravity of solids 2.7, we can compute the void ratio of a soil. The soil being saturated, E is equal to WGS will be valid. So, from this concept we can determine E. From there porosity can be calculated as N is equal to E by 1 plus E. By using relationship between seepage velocity and discharge velocity, the relationship what we derived in the previous classes is Vs is equal to V by N. By using the computed value of N, computed value of discharge velocity, we can calculate seepage velocity. So, this is the how the problem works out. What we are required to determine is total vertical stress at elevation A, B and C, pore water pressure at A and B and C by considering the upward flow, because the sand layer below is under artesian conditions. Now, let us look into the permeability and drainage characteristics of soils. permeability and drainage characteristics of soils. Before introducing the methodologies for determining the permeabilities in the laboratory, let us look into the ranges of the values of the permeabilities of soils. So, coefficient of permeability K meter per second, which is given here. The zone with the yellow is shown with a permeability ranging from 10 to the power of 0 to 10 to the power of minus 6 meter per second, and the zone with pink color, which is shown from ranging from 10 to the power of minus 6 to 10 to the power of minus 8 meter per second, and practically impervious zone, which is indicated with orange color, is 10 to the power of minus 8 to 10 to the power of minus 11 meter per second. So, you can see the range of the values of the permeability. For a sandy type of soil or a gravelly type of soil, the permeability is as high as 1 meter per second. For a clay type of soil, a pure or homogeneous clay type of soil, the permeability can be as low as 10 to the power of minus 11 meter per second. So, the contrastation behavior could be attributed to the soil type, which we will be discussing during the latter part of the lecture. So, here from the drainage point of view, many times we are required to select a particular material for performing drainage. For example, under parking lots or under footpaths or under market yard pavement paths or and below the subgrade, road subgrade. So, here the drainage, which is very important in such type of locations. So, here the good drainage conditions for a soil can prevail if the permeability is in the range of 10 to the power of 0 to 10 to the power of minus 6 meter per second. One can see the tendency of decreasing the susceptibility for having qualification for as a good drainage material decreases in this direction. Here poor in this region from 10 to the power of minus 6 to 10 to the power of minus 8 meter per second, and practically impervious from 10 to the power of minus 8 to 10 to the power of minus 11 meter per second. Here the type of the soils which will come in this particular zone, they are clean gravels or clean sands or clean sand with gravel mixers. So, if you have got a clean gravel and clean sands and clean gravel and sand mixers, then they can be qualified as to some extent as a good drainage material. In case if you have very fine sands, organic and inorganic silts, mixers of the sand, silt and clay like glacial till, and stratified clay deposits. So, stratified clay deposits in the sense like walled clay deposits. In those cases, the permeability requirement is 10 to the power of minus 6 to 10 to the power of minus 8 meter per second, and the qualification as a drainage material or a rating is a poor. And here homogeneous clay below the zone of weathering can have permeability in the range of 10 to the power of minus 8 to 10 to the power of minus 11 meter per second, and this can be a practically impervious material as far as the drainage point of view. But this particular property can be used or is being used for constructing barriers for preventing the migration of pollutants or contaminants. So, measurement of the soil permeabilities. This particular slide we have already seen. Let us look once again into this particular slide. The value of the coefficient of permeability K depends upon average size of the pores and is related to pore particle sizes and their packing. So, here the larger particles can have larger pore spaces and smaller particles can have smaller pore spaces. So, here average size of the pores and it is related to the particle size and their packing, and particle shape, it can be angular or subangular or rounded. So, we have discussed earlier the particles with a rounded arrangement can have large pore spaces. So, in those cases if the permeability can be high. For example, if the particles are with subrounded or angular in shape, then they can have a different, it can have the flow can be affected because of the interaction of the water when it is flowing through those pore channels, passing through particles having angular shape. And the soil structure, that is the arrangement of the particles. In case of a single grained structure for bulky particles, it can have two extremes like loose arrangement and dense arrangement, or in the case of a natural arrangement, it can be medium dense or medium very dense arrangement. So, depending upon the arrangement, it can have the effect on the permeability. When it comes to this soil structure for fine grained soils, it all depends upon the physico-chemical environment surrounding the particles. So, that can influence the permeability value to a large extent. So, here if you look into this, what we discussed in the previous lecture, the ratio of the permeabilities of typical sands and gravels to those of typical clays is of the order of 10 to the power of 6. As we have seen in the previous slide, the clay and the sand have got a distinct difference in the permeability values are concerned. So, typical sands and gravels to those of the typical clays is of the order of 10 to the power of 6. So, 1,000,000 times the difference can be there. So, a small proportion of the fine material in a coarse grained soil can lead to a significant reduction in the permeability. So, if a small proportion of the fine material or fines content can influence the coarse grained soil in reducing the permeability. So, let us look into the methods for measuring the permeability. We have discussed that there are number of tests can be used to measure or estimate the permeability. Laboratory methods, basically the two methods which are popular, they are, one is constant head test, which is basically used for highly permeable soils, and other method which is called falling head test, which is basically used for relatively impermeable soils, which is meant for clay soils or silty clay or silt and clay mixers. Indirect methods for computation from the grain size distribution and iodometer test. In the field methods, we have discussed, we have introduced like two methods we have discussed. One is pumping methods and borehole methods. Particularly, the Pekus tests are very famous. So, here we are not discussing about the field methods, but there are field methods which are available based on the pumping tests for a unconfined layer or a confined layer under an impermeable layer and or a under an permeable layer. So, Pekus tests are very famous in determining the permeability value in the field. Let us discuss about the two laboratory methods called constant head test and variable head test or falling head test for determining the permeability in the laboratory. And indirectly, for a typically clean sands or mixers of silt and sand to some extent, the determination of the permeability by using a correlation between an effective particle size and coefficient of permeability is very useful in estimating the permeability value. Before looking into the laboratory measurement of the permeability, the two important aspects which are required to be understood or have to be ensured have to be discussed. So, in this slide, in determining the permeability of coarse grained material, large quantities of flow occur in short periods of time. Because of the large pore spaces, the large quantities of flow occur in a short period of time. Contrary to this, in case of fine grained soils, small quantities of flow occur over long periods of time. So, there are two distinct differences are there. In case of coarse grained soils, large quantities of flow occur over a short period of time. In case of fine grained soils, small quantities of flow occur over a long period of time. So, two aspects that need careful attention for all types of soils are, the first aspect is to ensure that the flow occurs only through the soil, not at the interface between soil and the mold in which the soil is contained. So, here to ensure, one has to ensure that the flow occurs only through the soil, not at the interface between the soil and the mold in which the soil is contained during the permeability test. And the soil sample is fully saturated before recording observations. So, this has to be ensured. The importance of saturation of the sample is very much required. Otherwise, the air which is there in the soil voids, the voids of the soil mass can influence the permeability value, can hinder with or can influence the flow channels which are developing through the soil mass. So, here the two aspects, one is to ensure that the flow occurs only through the soil, not at the interface between the soil and at the mold in which the soil is contained, and the soil sample is fully saturated before recording observations. So, the one of the first methods for determining the permeability of relatively permeable soils, basically the soils which are coarse grained in nature, they are determined by using constant head permeability test. The setup for this is explained in this slide. It shows like this: a soil sample having a thickness having L, which is shown here, and which is surrounded by two porous stones. One porous stone is placed above and one porous stone is below, and it is a constant head water level is maintained as shown here in this figure. The extra surplus water is collected here, and here is the water level is maintained here. So, here because of this the flow occurs with an hydraulic gradient H over L. So, this flow occurs in the downward direction. So, here a relatively sandy soil is shown, and A is the area of the cross section of the specimen perpendicular to the direction of the flow. A is the area of the cross section of the specimen perpendicular to the direction of the flow. So, this is an arrangement for constant head test. So, here let us look in order to calculate the flow or coefficient of permeability. What one has to do is that after establishing a steady state seepage conditions, what one has to do is that collect a known amount of water, amount of water say in Q in a given time t. For a given time t, suppose we collect a amount of water in a measuring jar is say Q. So, based on that by using the relation theory of continuity equation, we can say that Q is equal to AVT, where A is the area of the cross section over which the flow is occurred, and V is the discharge velocity with which the flow is taking place, and T is the time over which this flow Q has been collected. I is the hydraulic gradient, which is nothing but H over L. L is the length of the specimen, and H is the one head which is driving the flow. So, the head loss between these two levels is H. So, Q is equal to AK into H by L, that is V is equal to has been substituted by adopting the Darcy's law conditions Ki, K which is the coefficient of permeability, I is the H by L and time t. So, after rearranging we can write K is equal to QL by AHT. So, by this by following this method, by repeating the similar experiment for 3 or 4 times, then average value of the coefficient of permeability K can be determined. So, this is basically a method for coarse grained soils. So, this has to be conducted either on the disturbed samples or on the remolded samples, and it is possible it is not possible to perform this particular test on undisturbed samples. The main features of the constant head test, if you look into it, it is suitable for soils having coefficient of permeability in the range of 10 to the power of -2 to 10 to the power of -5 meter per second. Like as we introduced previously, it should have the permeability in the range of 10 to the power of -2 to 10 to the power of -5 meter per second, which applies to clean sand and sand gravel mixers with less than 10% fines. So, the fines cannot be more than 10%. If it is more than, then the variable head test or falling head test has to be considered. It can be suitable for soils when used in their completely disturbed or remolded states, such as for drainage materials and filters, to confirm that their performance would be adequate. So, many times it is required. So, this is performed by checking or qualification of this particular materials as a drainage materials or a filter materials. So, the main features of constant head test is basically used for coarse grained soils or soils having permeability in the range of 10 to the power of -2 to 10 to the power of -5 meter per second, and which applies to clean sand and sand gravel mixers with less than 10% fines or so. So, it can be suitable only for soils when used in their completely disturbed or remolded states, such as for drainage materials and filters, to confirm that the performance will be adequate. So, having seen the constant head test for determining the permeability of coarse grained soils in the laboratory, let us look into the variable head or following head test method. Here, this particular arrangement which is shown here, he is having a soil sample which is relatively impervious, a clay soil sample which is placed at a certain unit weight and water content and surrounded by two porous stones, one above one is placed above, one is below, and it is connected with a stem having a tube having a area of cross section A, and it is bottom portion is connected with a stem which is shown here. So, cross sectional area of the standpipe which is connected to this particular arrangement is say A, that is this cross sectional area, that is having a small diameter d, and here A is the cross sectional area of the soil or which through which the flow is occurring. Now, let us assume that at time t is equal to 0, the head is h1, at time t1 the head is say h2. That means that at time t is equal to 0, the head is h1. Now, at time t is equal to t1, the head is now h2. So, there is a drop of the head from h1 to h2. So, let h be the head of the water at any time t. So, let in time dt the head drop by amount dh. So, here assume that let h be the head drop in at any time t. So, dh is the small head drop in a small time dt. So, by using this delineation now, let us try to bring out a theoretical deduction, so that we can determine an expression for determining the coefficient of permeability based on falling head test. So, here if you look into it, by dropping amount of water from H1 to H2, minute amount of water is trickled into the soil. So, in here what we look into is that the water which is passing into the soil. In case of constant head test, what we establish is that water which is passing through the soil. So, the amount of water which is flowing into the soil is very less in case of falling head or variable head tests. Here, now considering the previous discussion, the quantity of the water flowing through the sample in time dt from the Darcy's law can be estimated like this, like we did in the constant head test. dq is equal to kia dt. So, dt is the time or which that head loss dh has occurred. So, dh is the small head and h is the head at time t. So, dq is equal to k into I is equal to h by L. A is the cross section area of the sample and dt is the time. So, k into h by L into A into dt. So, this quantity of discharge can also be expressed as minus A dh, where dh is the small drop which has occurred in over a time dt. So, this is negative because as the time increases, head decreases. So, because of this, it is expressed as small discharge dq is equal to minus A into dh, where A is the cross section area of the sand pipe which is above the system which is shown in the previous slide. Now, equating this quantity of the discharge which is dq is equal to minus A dh and dq is equal to k h by L A dt, and integrating between the heads h1 and h2, where h1 is the head at t is equal to t0 and h2 is the head at t is equal to t1, over the small change head is dh, ka by L where the time is t is equal to t0 to t1. By simplifying and rearranging, we will get k is equal to 2.303 AL by AT log to the base 10 H1 by H2. So, by using this expression, one can determine the permeability of fine grained soils, especially clay soils, by using variable head test or falling head test. So, here A is the area of the cross section of the standpipe, L is the length of the sample, and capital A is area of the cross section of the soil sample through which the flow is taking place, and T is the time over which the difference in heads H1 and H2 is measured. So, by repeating this particular experiment for 2 or 3 times, an average value of the coefficient of permeability can be determined and can be reached. So, these permeability values what we determined by using this method, they can range from 10 to the power of minus 8 meter per second to 10 to the power of minus 11 meter per second. So, this is a procedure how we have to determine the falling head test permeability of a given soil, particularly a fine grained soil, by using falling head test. So, main features are the major differences between constant head test and falling head test can be classified like this. In the constant head test, permeability is computed on the basis of the fluid that passes through the soil sample. So, in the constant head test, the permeability is computed based on the amount of the fluid or permeant that passes through the soil sample, while in the falling head test, K is computed, that is coefficient of permeability is computed on the basis of fluid flowing into the sample. So, here the amount of discharge that is the flow which is taking place into the sample. So, with the constant head test, time is required to accumulate the fluid volume necessary to perform computation. Extreme care would be required to prevent leaks in the apparatus and evaporation of discharged water. In case of the falling head test, the duration of the test is shortened and care is required to prevent evaporation of water in the inlet tube. So, evaporation of the water in the inlet tube can influence the results. So, that has to be taken so that the evaporations are minimal. So, having seen the laboratory methods, and we as mentioned, there are also methods for determining permeability in the field like pumping tests or borehole tests. The Pekus tests are famous. We are not discussing these methods for determining permeability in the field. After having introduced now the measures methods for measuring permeability, let us look into the various factors which can influence the coefficient of permeability. So, these factors affecting the permeability can be understood with the help of the two basic equations. They have been postulated by using that interconnected voids are visualized as a number of capillary tubes through which the water can flow. So, all these interconnected flow channels are assumed as a thin capillary tubes or through which the flow is taking place. So, all the interconnected tubes have been assumed as a capillary tube or so through which the flow is taking place. So, the first to give is one expression, that is Kozny and a Karman equation, where he has included the many aspects or many factors which can influence the permeability. So, this is expressed in the form of a Darcy's equation V is equal to Ki. So, this particular part is nothing but coefficient of permeability K. Another equation reflecting the influence of permeant and soil characteristics on K was proposed by Taylor in 1948 using Poiseuille's law, which is shown here, which is which can be read like this: V is equal to C into d square gamma w by mu E cube by 1 plus E and I. So, if you look into this here, first Kozny and Karman equation, this equation was proposed by Kozny-Karman basically for coarse grained or gravelly soils. V is equal to 1 by Cs SS T square and gamma w by mu E cube by 1 plus E I. So, both the equations assume the interconnected voids and are visualized as number of capillary tubes through which the water flow is occurring. So, we will discuss this Kozny-Karman equations in depth, and based on that we will erupt or evolve at the factors affecting permeability. So, factors affecting permeability, and in the case of Kozny-Karman equation, so here these are the soil is assumed as assemblage of particles, and the flow can take place through in a microscopic way through a Tortillas path. So, this particular path or this particular length of the flow passing through these contact points of the solid grains is called Tortillas path. So, the tortuosity is defined as the ratio of the tortuous length to the imaginary length which is assumed as flow through soil which can pass through the voids as well as to the solid grains in imaginary length. So, that length is L. So, the tortuosity is nothing but ratio of L1 by L. So, which is indicated here in this Kozny-Karman equation as T. So, it can have a different tortuous lengths passing through these contact points and through the voids in the soil mass. In the Kozny-Karman equation which was introduced in the previous slide, where the V is the discharge velocity, Cs is the shape factor, C suffix S is the shape factor. This is for granular soils, it is Cs is equal to 2.5. SS is the surface area per unit volume of the solids. and T is the tortuosity factor, which is root 2 for granular soils. And this particular Kozny-Kármán equation can be simplified as K, which is Darcy's coefficient of permeability, as K, which is capital K times gamma W by mu. So, here the capital K, which is defined as intrinsic permeability or absolute permeability, which is a function of soil skeleton and which is constant for a particular soil type, So, here the K, which is function of 1 by which is nothing but the K which is indicated here in this equation is nothing but 1 by Cs and SS and T square and E cube by 1 plus E. So, here the units for the K are indicated as Darcy's. 1 Darcy is equal to 0.987 into 10 to the power of minus 8 centimeter square. So, the absolute permeability units are nothing but they are centimeter square or Darcy's. So, this is basically is a property of soil and which is a function of the soil skeleton, So, the relationship between K, which is coefficient of permeability, and absolute permeability is K is equal to capital K times gamma W by mu. So, if you look into this with an increase in viscosity, then the coefficient of permeability can be less. And if you look into this particular absolute permeability value, any change in water ratio, then change in the absolute permeability, and the tortuosity and then the specific surface area and then shape factor have got which are included. So, that is how this is indicated as which takes care of the soil skeleton properties. So, list of factors affecting permeability, if you indicate, then they can be listed like this: shape and size of the soil particles. One is the shape and size of the soil particles, and void ratio, that is K. As void ratio increases, K value increases. That means that the soil with higher void ratios can have higher permeability. Degree of saturation, that is K increases with increase in value of saturation. So, at partially saturated soil, because of the entrapped air within the voids, can have low permeability. Composition of these soil particles, particularly for clay soils where the mineralogy will come into the picture to a large extent. Particularly for silts and sands, the mineralogy may not influence in a big way. Soil structure, that is the type of arrangement, whether it is single grained or in case of clay soils, whether it is a fine grained soil, whether it is a flocculent structure or dispersal structure, matters a lot. Or compactive effort, that is the one which is not listed here and which is also can influence the permeability. And viscosity of the permeant or density and concentration of the permeant. So, these are the factors which can influence the coefficient of the permeability. And we also discussed that in the based on the Taylor's equation, one relationship between the K is proportional to dE square, which indicates that with an increase in grain size, then increase in the permeability value can be seen. That is that if dE happens to be an effective particle size, a large effective particle size can have the larger permeability. So, that is the one which is now discussed, is that factors affecting permeability, the effect of the grain size. So, Hazen he has proposed a relationship between or a correlation based on permeability values determined with sands or soils which are having a different effective particle sizes. So, this particular graph which is shown on here, D10 which is plotted on logarithmic scale and coefficient of permeability K in meter per second which is plotted on the y axis is shown here. Different soils like silt and silty sand, sand with fine, medium and coarse and gravel are selected. And here once the values are plotted, the linear the regression which has been obtained indicated the equation, which is the regression equation is named here as Hazen's equation after William Hazen, is K is equal to CD 10 square, where C is equal to 10 to the power of minus 2 then we can determine the coefficient of permeability in meter per second if you use C is equal to 10 to the power of minus 2 and D10 in mm, we can determine. So, this equation which is indicates that the larger the effective particle size, the larger is the coefficient of permeability, and this particular relation is basically valid for K value for clean sands or sands with silts less than 5% fines or so. So, C is a constant which includes the effect of the shape of the pore channels in the direction of the flow and total volume of the pores. So, C is the constant which includes the shape of the pore channels in the direction of the flow and total volume of the pores. So, this is a very important equation as far as for determining the coefficient of permeability based on the particle size distribution. So, by using from the this is the one of the significance of the particle size distribution we have discussed while discussing about the CV analysis or a particle size distribution of soils. So, here the Hazen's empirical relationship is shown here, which is nothing but Ka is equal to CD 10 square, where C is a constant which is obtained from this regression. So, here if you see the zone which is circled here, which is highlighted here shows silt and sandy particles. So, this is where the large samples which are points which are there. So, that is the reason why which is said that it is valid for sandy soils. And another question is that why the D10 is only selected. So, if you look into this, because the D10 is selected because the smaller particles control the size of the pore channels. Suppose if there are large particles are there is a chance that these large particles which are having large pore spaces can be filled with small particles, then pore space can be reduced. So, that is the reason why the well graded sand and uniformly graded sand, the well graded sand have low permeability compared to the uniformly graded sand. Uniformly graded sand have got, because of the large void ratio, will have large permeability. So, in factors affecting permeability, we are discussing about the effect of grain size. The permeability of the granular soils depend mainly on the cross sectional area of the pore channels. That is what we have discussed, and we are highlighting once again that the permeability of the granular soils depend mainly on the cross sectional area of the pore channels. Since the average diameter of the pores in a soil at a given porosity increase in proportion to the average grain size, the permeability of the granular soils might be expected to increase as the square of the sum of the characteristic grain size. That is the reason why in the Taylor 1948 he has used K is proportional to around DE square. That is how the Taylor's equation what we discussed earlier has K is proportional to DE square. Now, factors affecting the coefficient of permeability, the another factor is the degree of saturation. If you look into it, K is proportional to SR. At low saturation, there will be reduction in flow channels available for flow. So, here after DAS 1987, the chart which is shown here is degree of saturation on the x axis and coefficient of permeability on y axis in mm per second is shown here for a medicine sand with E is equal to 0.797. As can be seen, with an increase in the degree of saturation, increase in the coefficient of permeability can be noted. So, with an increase in degree of saturation, increase in the coefficient of permeability can be noted. That means that the air which is trapped inside the soil voids is getting shunted out, because of that the permeability value increases. The another important parameter which influences the permeability is the soil structure. The permeability of the soil deposit is significantly affected by its in place soil structure, that is in situ soil structure. A loose granular soil would have a higher void ratio than a dense soil and therefore would permit greater flow. That is the reason why we have discussed that well graded sand and uniformly graded sand. The well graded sand have low permeability compared to the uniformly graded sand. That means that the gradation or particle size composition also very important for if you consider the flow through a soil. A fine grained soil with flocculent structure will have higher permeability than soil with dispersed structure. So, this we have discussed by discussing about the compaction characteristics of soils. So, here if you connect back that for a given compactive effort, if we have got say fine grained soil with a flocculent structure and dispersed structure, the soil with the flocculent structure have got more permeability than dispersed structure. In case of flocculent structure, the more or less we will get the isotropic condition, the permeability will be same in all directions, the flow will be less tortuous. In case of a dispersed structure, the flow is more of anisotropic in condition, the horizontal permeability is different from vertical permeability. That means that the flow which is taking place perpendicular to the direction of the this orientation of the plates in the dispersed case, they are face to face orientation, which are parallel arrangement, that indicates that the flow will be more tortuous. That means that more time it takes to flow in the perpendicular to the plane of the orientation of the plate particles in dispersed structure, rather than the flow across the this particular plane, that is along the plate shaped particles. So, the permeability in along the plate shaped particles will be very high compared to its perpendicular direction. So, here the same topic what we discussed here as shown here. A fine grained soil with flocculent structure will have higher permeability than soil with dispersed structure. So, here the soil with the dispersed structure is shown here. So, here the flow normal to the particle orientation is found to have a more tortuous path and leading to a very low permeability in this direction, compared to the flow parallel to the particle orientation. If you consider, it is less tortuous, can have more permeability. So, the dispersed structure will have a low permeability and overall compared to flocculent structure, and also the flow is anisotropic in condition. So, horizontal permeability is different from vertical permeability. The horizontal permeability which is in the direction of the or parallel to the orientation of particle is very high compared to the vertical permeability, that is flow normal to the particle orientation. So, even at similar void ratio, a clay with an undisturbed flocculate structure will possess large void openings than the same clay having dispersed structure. So, we have also discussed like a flocculent structure can have more because of the truss like arrangement, have got a 3-dimensional or random arrangement having with a large opening or spaces or large pore spaces. So, larger the pore spaces, the more is the flow. That is what we have discussed. K is proportional to the D, which is the size of the pore spaces. In case of dispersed structure, because of the orientation in which they are as a random arrangement which takes place, where the face to face orientation takes place, and because of that the less flow takes place for the dispersed structure, and then low void ratio prevails for a dispersed structure. That means the low void ratio in the sense for the compared to relatively when you compare with the flocculent structure, the flow will be very less in case of dispersed structure. So, here flow through the clusters of the particles of clay soil is shown. So, because of this particular region, we can have a flow path can be like this and can be like this. So, these are the clusters of the clusters or packets of clay particles are shown. So, because of this the soil with flocculate structure or flocculent structure exhibits isotropic conditions, the permeability will be same in all directions. In case of dispersed structure, it exhibits anisotropic conditions, and the permeability of soil is severely affected by the type of the structure. Similarly, another factor which is required to be discussed is the compactive effort. Like we discussed, like it can be in case of granular soils or sandy soils, it can be loose compaction or dense compaction. In case of clay soils, as we have already studied, it can have a low or reduced compaction or Proctor compaction or standard Proctor compaction or modified Proctor compaction. So, if you look into it or if you recall, the variation of gamma D versus water content can be obtained like this. This is for the reduced compaction, and this is for standard Proctor compaction, and this is for modified Proctor compaction. With an increase in compaction energy, there will be decrease in the optimum moisture content, increase in the dry unit weight, and this line is the 0 Edwards line. So, if you select for a particular standard Proctor compaction, the structure can be somewhat like this, here flocculent and here it can be dispersed. So, by using the same logic what we discussed, the flow which is on the permeability value on the dry side of optimum will be very high compared to the flow on the similar but soil with the same identical same void ratio or same dry unit weight. The soil with a flocculent structure can have higher permeability compared to the soil with a dispersed structure. The discussion we have already had is because of the type of the soil structure prevailing at that particular void ratio. So, with an increase in the compactive effort, the K value decreases. That means that like modified Proctor compaction can induce more packing of the soil particles. So, because of that, the permeability value decreases. So, similarly, on the wet side of the optimum, the permeability value decreases. So, if you look into this particular relationship by using this particular expression, what we are discussing is gamma d and water content. Then you got a Proctor compaction curve. This is the maximum dry unit weight and optimum water content. So, if you plot the permeability value here, K, which is in meter per second, and water content. So, this side is dry side of optimum and this is the wet side of optimum. So, here on the dry side of optimum, the soil can have high permeability and the permeability value decreases for a given typical soil. So, on the wetter side of the optimum, the coefficient of permeability will be less. On the dry side of optimum, the coefficient of permeability will be high. So, thus that reason is attributed to, this particular region is attributed to the type of the soil structure which is prevailing at that particular moist compacted state or in its natural state. So, this is how what is happening is that as we increase the water content in, say, for example, for compaction process, the orientation of the particles changes. That is that the structure is gradually transforming from flocculent to a dispersed structure. So, as we increase the compactive effort, then this also shows that on the dry side of optimum there is a decrease in the coefficient of on the dry side of permeability value will also be less with an increase in the compactive effort. Similarly, so if I take this for a modified compaction, so this is for say a standard Proctor compaction. With modified compaction, it can have a value slightly less compared to this standard Proctor compaction. So, the increase in compactive effort decreases the coefficient of permeability. So, here again we connected back to the type of the soil structure which is prevailing in that moist compacted state for a given soil. So, having seen the compactive effort, now let us look into the effect of soil type. That is, the volume of the water that can flow through a soil mass is related more to the size of the void openings than the number or total number of voids. So, the K of the coarse grained soils is greater than K of the fine grained soils. That is the reason we have to understand, particularly by keeping in view of the surrounding environment around the particles. That is environment surrounding the particles. So, K coarse grained soils is greater than K fine grained soils, even though the void ratios are frequently greater than for fine grained soils. So, though the void ratios are very high for fine grained soils, we always see that the K of the coarse grained soils is greater than K of the fine grained soils. The reasons, because we have seen that the void ratio, as the void ratio increases, the permeability value increases, but it will not happen like this for coarse grained soils and fine grained soils. That means that there are another additional factors which are influencing this particular behavior. So, K of the coarse grained soils is a function of particle size, gradation, particle shape, roughness and void ratio of the soil medium. If it comes to the K of the fine grained soils, that is a function of type of the clay mineral and adsorbed ions surrounding the clay particles. Where here the particle forces dominate this particular arrangements. So, here the reasons let us discuss why the K coarse grained soils is more than K of the fine grained soils. So, by effect of the soil type, if you look into it, the concept can be assumed and explained by using the flow through a conduit pipe. So, this is for a coarse grained soil or a sandy soil, where you can see here the flow is V maximum is occurring at the center and V minimum is occurring at the wall. So, this is how the flow takes place. So, this particular variation is attributed to the frictional drag at the edges as well as some viscous drag which is taking place when the flow is taking place through the sand grains. So, this is nothing but the pore space or the pore channel diameter through a sandy soil. When it comes to clay soil, as we all know, we have a clay particle. If this is the surface of the clay particle and this is the another clay particle having a shown part of the adsorbed and double layer water is shown here. So, this situation is different. So, here where this is particular coating of adsorbed water layer is absent in case of sandy soil. So, here in this case, as you can see here, flow through pore channel in a clay soil with more developed depressed double layer, developed double layer. In case of here, suppose if the layer is depressed because of some cation exchange which is taking place, because of that there can be more water flow because the double layer is depressed here, which is shown here. In case of double layer is fully developed, then we will see that the less water flow takes place. The reasons we will discuss in the next slide, where we are trying to explain this particular phenomena of having K for coarse grained soils of soil through the concept of flow of water through a conduit. So, if you look into this here, this particular distribution is attributed to friction developed at the conduit wall and the viscous friction developed in the moving fluid. So, because of this region, what will happen is that V occurs maximum here and then minimum here. So, some energy is lost here. But whereas in case of the flow of water which is taking place through the clay particles, one reason is that the frictional drag which is taking place, the flow is attached almost to the wall, and because of that very less flow occurs. In addition to that, the adsorbed ions will try to keep the water in that very close to the clay particle. Because of that, the flow which is taking place through this fine grained soil is very less. So, here the same concept is explained here. For fine grained soils, when void spaces are very small, all lines of flow are physically close to the wall of the conduit, and therefore only low velocity flow occurs. So, mostly the velocity of the flow occurring along the boundaries of these double layers which are there. So, depending upon the development of the double layer, whether it is depressed or completely, that also influences the flow condition. In case of a depressed double layer, the complete more flow occurs compared to relatively more flow occurs for a completely developed double layer. In clays, flow in already small channels is further hampered because of the sum of the water in the voids is held or adsorbed to the clay particles, reducing the flow area and further restricting the flow. So, what happens is that in case of the clays, to the reasons are particularly clays or fine grained soils, because of the type of the environment surrounding the particle, that is physico-chemical environment surrounding the particle influences the flow conditions. In case of sandy soils, and this is not absent because of the loss of the frictional drag which is occurring at the edges, except that the velocity is maintained with the high flow is maintained. So, because of that, when the flow is high, that is seepage velocity is high for a coarse grained soil than for a fine grained soils. Because of this region, the soils particularly with sands are basically forming coarse grained soils, they exhibit very high permeability compared to fine grained soils. So, we can say that hence the K of the clay is very less compared to K of sand. So, another factor which is discussed is the effect of the permeant. Like as you have seen, K is proportional to gamma W by mu. So, variation of the gamma W with temperature is negligible. So, we can see that as mu increases, the coefficient of permeability decreases. So, higher mu, the lower coefficient of permeability. So, effect of specific surface area, if you look into it, we have discussed in the Kozny-Korman equation, K is proportional to 1 by SS square, where higher the specific surface area and low is the permeability. That means that depending upon the type of mineral, for example, kaolinite, mantomilite and illite, the kaolinite has got lower specific surface area compared to mantomilite. So, that means that the soils which are having mantomilite can have low permeability compared to soils which are having kaolinite. Similarly, the quartz which is having very low specific surface area exhibits very high permeability with this particular relationship. So, based on the discussion what we had, we can classify the soils according to their coefficient of permeability. The degree of permeability high, medium, low, very low or practically impervious can be said like this. High, we can say that if the permeability is 10 to the power of minus 3 meter per second, practically impervious if it is less than 10 to the power of minus 9 meter per second. Low is 10 to the power of minus 5 to 10 to the power of minus 7 meter per second. So, in this lecture, what we tried to understand is that the methods for measuring the permeability in the laboratory and factors, different factors affecting the permeability, especially the compaction effort or type of the soil structure and soil type. That is where we have discussed about the flow of water through conduit, and we said that K of the coarse grained soils is more than K of the fine grained soils, though the wide ratio for the fine grained soils is more than coarse grained soils.